Let us continue. Okay. Oh no, not this. Yeah. All right. So yep. Like from last time, last time we mentioned, we're done with the Markov chain, right? And for the last two lectures, we're gonna talk about the Poisson process, right? Queuing model and Brownian motion. Okay. So there will be no problem set associated with these two lectures. Basically, I do have problem sets for them, but right, I don't think we have enough time. And at this stage, I don't think right there's enough time to go into them into depth in terms of problem sets anyway. So I rather here focus on the breadth. And so for that reason, there's no quiz either, right? We'll still take a 10-minute break in between, right? But the talks will basically, right, expository. We'll still ask questions, everything, right? But the materials won't be on the exam, won't be problem sets, that kind of thing. Okay, so what we have, right, is, well, I mentioned last time that you can, right, divide the stochastic process into state space, right, and time. So basically, the time can be discrete or continuous, and state space can also be discrete or continuous. So if both of them are discrete, then you have Markov chain, kind of, right? I mean, it doesn't have to be Markov, but basically Markov chain is the theory of discrete time, discrete space. And then you can move on to continuous time, right? And discrete state space. That's where you have queuing models, Poisson process, right? Because basically there we record the arrival time, right? The number of people having served, that kind of thing, which are discrete variables, right? And then finally, we move on to the continuous model, which is the Brownian motion. Continuous time, continuous state space, right? And so for the Poisson process, right? Well, actually, moving on to these processes, what you should pay attention to is the nature of continuous time, right? How it's used, how it's modeled, how it's dealt, because anything continuous is delicate, right? And the point of this lecture here is that the exponential is the cornerstone, right, to building up queuing models and Poisson process. And the reason, right, the number one reason is because of the memoryless property, right? Now, the point here is actually the memoryless property is more of a convenience, maybe, rather than a crucial thing, right? In other words, phenomenon doesn't have to have a memoryless property, right? Waiting time or survival time doesn't have to have memoryless property, but it's probably the easiest building block, right? Exponential random variable is a continuous random variable, so it fits right in, right, to the continuous time context. And the memoryless property, right here, which you should read, right, as both kind of Markov, because, right, it doesn't remember the past history, right, and time homogeneous, because, right, doesn't matter what this value t is the same, right? So memoryless and time homogeneous sounds a lot like Markov chain, right? And that's why basically, right, the exponential random variable is sort of like the first, right, basic building block that people use to build a queuing model and Poisson process. And this lecture can be viewed as, one way, right? Well, of course, it's going to be like everything you want to know about exponential random variables, right? Or everything you never know about the exponential random variable. But another way is it's kind of like a long lecture on the memoryless properties and its consequences and things like that, right? So that's the angle you should kind of look at this lecture as. So, right, the memoryless property allows us to basically forget the past and condition, right, on the fact you have survived, for you as in the waiting time, right, has survived a certain amount. It acts as if, right, it's renewed, from the start, right? So renewal theory, things like that, the term, right, comes in from this point of view, okay? So this quantity right here, as I mentioned, right, is the expectation of x over the range, right? That x is over t, not the conditional, right? Not the conditional one. So these are different, okay? So the conditional one, if you take expectation, it will give you the same, which is lambda, right? And sorry, 1 over lambda and 1 over lambda square, right? So yeah, okay. So let's kind of try to see the distinction. All right. So before we start, right, it's interesting to tell you that the geometric distribution also has memoryless property, right? Exactly in the same way that we phrase it above, right? So here, you could do m, right? N is m plus k, let's say, right? So this is k, right? So doesn't matter, right? If the geometric, right? And what's a good example here, right? Waiting, right? Of course, waiting for the first success, like the first return to a state or something, right? So it doesn't matter, right? How long you have waited, right? The probability you will have to wait like a certain extra times is as if you start from scratch, right? So this explains right, the deep connection, or deep or not, right? The connection between continuous time and discrete time, right? In the Markov chain, it's not that explicit, but the geometric structure is there, right, within the return time, right, to a state, to a recurrent state, remember? So exactly, right, that memoryless property, which we didn't point out explicitly, because there we have the Markov property, right, the strong Markov property to work along, but it's actually the same thing, okay? And so it explains that. Basically, that's why we have exponential, right, waiting time in the continuous time, because it exactly is the continuous analog of the geometric distribution, right? The second thing is that, well, does that contradict what we said before about, right, the only memoryless, right, distribution? Well, the key word there, right, is the only continuous, right, memoryless distribution. So if you throw in the word discrete, then geometric is it, right? And if you throw in the word continuous, then exponential is it. So, and this also probably explains why I think someone at some point kind of confused the two distributions, right? Because they kind of act in a similar way, but they live on different, right? Continuum, right? Any question about this? All right. So here's an example, right, of the benefit, right, of knowing the memoryless property, right? And this story has to do with basically, right, insurance payout and deductible, right? Every insurance payout, I think, has some kind of deductible, right? Meaning that they only pay you above and beyond a certain amount, right? So here in this example, let's say the deductible is 400, right? Just for the sake of discussion, right? And say if, right, the payout has an exponential distribution, which, right, you could question whether the exponential distribution is a appropriate, right, distribution for the payout, right? The payout is random, which is kind of correct, right? You never know how much the payout amount is, right? It depends on the nature of the event. But the fact that, right, the exponential is modeled as a payout amount is actually kind of okay, because, right, basically here's the amount, right? And here's the density of the amount, which really kind of says that, right, you have a high likelihood of paying quantities that is lower, right? And for the really large amount, that's a lower, right? I mean, chance, lower likelihood, right? Which seems to fit. I mean, right? That's how basically, right, accidents or whatever happen that way. But anyway, right? Of course, you don't have to use the exponential as the model, right, for payout. Could use anything else, but something else, right? But if you do use exponential model and couple with the deductible, then you have, right, a very easy calculation of the expected payout, right? The expected payout, which is this amount, right? By the way, which is really this coin right here, right? This coin right here, right? So this calculation, even though it's not this one, we can use the law of total expectation, right, to make a shortcut of it. So basically, right, condition on if you do payout, right, if you do payout, then you're gonna pay out right on average with the exponential lambda, because this is where the memories property is used. Right, and if you don't pay out, of course, the amount is zero. So the expected payout would just be, right, the average amount times the probability that you have to pay out, right, which is e to minus 0.04. 0.4. Does it make sense? So that's the kind of like a easy, right, or cute application of the exponential model in the model of insurance deductible. Any question here? Okay, right. So that's really just something to demonstrate. Here is really the question. We start with a queuing model, right? So this is a model.
Forgive me, but why do we have e to the negative 0.4? Why is it 0.4 in the exponent?
That's the probability that you pay out, right? That's probability y equals to 1, which is probability x bigger than 400. And because the rate is 1 over 1,000, 400 over 1,000 is 0.4. That's a probability that.
Okay. Thank you.
Yeah, this is like almost like a child's calculation. I'm not saying that it's easy or your question is not relevant, but it's more like you could easily deduce this without knowing that you do it right for some reason. That you say, well, the payout would be the expected amount of payout times the probability you have to pay out. And you think, okay, the expected payout is 1,000, so times the probability you pay out, which is e to minus 104. What you don't realize is two things. You use the law of total probability in the process, and B, you use the memories property in the process, right? But the point is that the answer is actually way too easy, but that's because of the property of the exponential. Right?
Thank you.
Mm-hmm. All right, so this right here is what we call a M2 model. Okay, not that you need to know this, but basically, right, there are two servers, and the arrival. Well, technically speaking, we don't even model the arrival here, so this first M is irrelevant-ish. So let's take that out even. So the first model the arrival time, but in this question we don't have the arrival because we only have 3 players in here. So that first is not there, right? But the second one talks about the server time, right? And so here, right, the two clocks serve at exponential time that independent of each other. That's the second M, okay? 2 is the 2 servers. The first one is not there because a queuing model would also model, right? People keep arriving in the post office. Here we're just really playing with a small sub-story, right? Which is like we have 3 players, right? 2 servers occupied, 1 arrived, that's it. Anyway, right? So here, and notice that in the queuing models in general, the servers don't have to have the same serving rate. Here they do, right? They have the same serving rate of lambda. Okay, so the 2 clerks serve at the same rate. Okay, so the question is, right, I can't show it. I mean, if you saw it, that's fine. But the question is, what's the probability that Mr. X will be the last to leave? Or if you ever come to the post office these days, right? I think that's probably some question on your mind, right? People just take forever to finish with their business, right? Well, what's chance that you are the unlucky one to be the last to finish? All right. So what do you think the answer here is, and why? Right? Why? Why that way? It's very important. There are a lot of like, you could easily stumble on the right answer here, and that's not like a terrible thing, but if you're not careful, right? If we change the context a little bit, then that right answer will be wrong. So we want to know why, right? In this case. Right? Is the question clear? At least, right? So Mr. X comes in, right? Mr. Y and Z is already there at the two server, right? And Mr. X is here, right? Waiting. And as soon as, right, one of them leave, Mr. X will come in, right? And then what's the probability he'll be the last to leave? The server will serve, right, each customer with an exponential time. And just so you know, right, these kind of questions, these kind of considerations are classic for queuing model. As in classic, as in people who are used to this kind of problem will just think about it very quickly. And of course, right, you're new to this, so if you don't think about it quickly, that's fine. But just saying that these are sort of like the techniques that people tend to use, right? So if you want to work in this thing for some reason, then these are techniques you want to pick up. Any guess?
It's
Yeah.
I'm still thinking about how to write it out mathematically, but it's the minimum of whoever finishes first, right? So it's the minimum between both exponential lambda and exponential lambda. What are they asking for? Is it a probability? Is it
probability Mr. X will be the last to leave. Does that make sense? So it's kind of clear, right? He will not be the first to leave, right? And well, he also, right, there's also this kind of model of non impatient customer, because there is kind of queuing model you see later on that people, when they wait too long in line, they leave, right? There's that. I mean, that's reality too. But here, right, we assume that Mr. X will wait as long as it needs, right? But yeah, right. And as soon as a spot opens up, he'll come in, right? And then we ask what throughout this whole process. So basically, he's the one to finish behind Mr. Y, Mr. Z. Right? Clearly, he will be right, not the first to leave. But what's the probability he will be the last to leave? Or is the question clear to begin with? All right, is the context clear? Is what we want clear? All right, let's ask an easier question here in this case. What's the probability Mr. Y is the first to leave? If we ask that question, what's the probability Mr. Y is the first to leave? What would the answer be?
Would it be 1/2?
Yeah, right, because they're kind of symmetric, right? So Mr. Y, Mr. Z have the same rate of serving, right? And independent, so 1/2 each, right? So like that, right? Mr. Y is the first to leave is 1/2. Now, of course, right, that's not the same as asking the problem Mr. Y is the last to leave, right? Notice these are not complementary. Agree? Probability, let's go here, right? Because we don't need the slide. Mr. Y, Mr. Z, Mr. X here, right? Probability Y first to leave is 1/2. Probability Y is last to leave, well, whatever, right? But notice that these two events are not complementary, right? If Y is not the first to leave, doesn't mean he's the last to leave, right? Things like that. But here we want probably Mr. X as the last to leave. Okay. Any guess? Last chance.
I want to say it's still 1/2
Okay. Explain your reasoning.
because if Mr. Y is the first to leave at 1/2 and then Mr. X takes Mr. Y's spot, it would be Mr. X and Mr. Z, and they would both still be 1/2.
Okay, not bad, not bad. But in your argument, there are a bunch of questions to ask. The first thing is you say if Mr. Y is the first to leave, right? I guess you would probably say, well, the same thing what happens if Mr. Z is the first to leave, etc. Right? All right, fine, we can live with that. But you probably have to say, right? You kind of do a lot of total probability there, which is okay, right? Now, then you say, then Mr. X comes in, and Mr. X and Mr. Z will still be 1/2. But why? Because notice, right? Let's say in your story, right? Mr. X comes in fresh. Mr. Z has been being served for a long time. Why is that still 1/2?
That's by the memorylist property, right?
Exactly, right? So along this line, right? Exactly that when Mr. X comes in, as far as Mr. Z is concerned, right? All this precious time he spent at the window doesn't count, right? I mean, as in for the future when he's going to finish. So that's exactly where the memorylist property comes in, right? So yes, the answer is correct, 1/2, right? Now, but if you want to write down carefully, blah, 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 right? You could, but notice that if you write down using the minimum and things like that, that will be very much intractable, right? So yes, the short answer is 1/2. And this is where the annoying thing about this kind of thing is that you tend to kind of use a short argument like that. Oh, 1/2 by memorylist property, all right? But pay attention on when it's used, right? And if it's used correctly or not, as we'll show you a lot of pitfalls, right? As in these follow-up questions. Okay. To test your understanding, what if, right, the two clerks have two different rates, which is more realistic now, right? Lambda, same question, but now if they have two different rates, and right, another question will be, I guess there's a typo here, right? You switch the role of the three guys, right? Here, Mr. X comes in with Y and Z here, but what if Mr. X is here, right? So you could ask, right? I guess we can preserve the same question, but like Mr. Right actually is exactly right the question I was saying here, right? What is wrong with Mr. Y will be the last to leave in this context, right? Okay. So think about those two questions, right? Or maybe, right? Let's exactly use this, right? So the first question is, what if they have rate lambda 1 and lambda 2? How would the question be different? And B, right? What if, we switch the role, right? X, Z, and Y, right? We still ask for X last to leave. Now, we're gonna discuss these things, right? But just to kind of make you see why, right, the next few discussions are relevant, let's see if you can try to guess the answers here and what your reasonings are or what you need to answer these questions, right? So you will appreciate, right, the materials will, the techniques we're going to mention next. Whichever one you want to pick, right? Let's pick A first. What if with the same setup, right? What if the clerks have different rates? How would the answer be different? I mean, you don't have to give the exact answer, right? Just point out the difficulty is good enough. Then, you know, we can investigate that difficulty, right? But if the clerks have different rates, then what's the main difficulty?
Are we assuming they're independent?
Yeah. I in all of these queuing models, as far as I know, right? I don't think people. I guess you could have a dependent server model. That would be very interesting, but that probably is very hard. Not very hard, but that would be very different. Yeah. No. The classical model, right? Servers are independent and everything is independent, right? I think the most I see, right, or at least not the most, but like at least the generalization I see is when they change the rate to be like dependent on time, the non-homogeneous version. Dependent servers is definitely something interesting. I haven't. I guess that's for more advanced queuing model or more advanced class, right? Focusing on queuing model. Yeah, independent. Everything is independent. So the main difficulty
I'm
here is
assuming you have to use the PDFs. You have to do it by actually examining the probability that the time that Y first finishes is less than the time that Z first finishes. And we have to use both exponential PDA.
Right. So here, right, the symmetry is no longer there for part A, right? So it boils down to you have to kind of calculate something like this. Because that's part of your conditioning, right? Because let's say this is lambda 1, this is lambda 2. Then if Mr. Y finish first, then X will go into the server, right, lambda 1 with this probability, right? If Z finish first, then X will go into the server lambda 2 with 1 minus this probability, right? So at the very least, we have to figure that out, meaning we have to compare, right, the two exponentials when they're independent, correct? So that's at least, right? And then like Kathy pointed out, maybe have something to do with the PDF. That's correct, right? So that, good, right? So that's one thing. And just to point out, right? Maybe, right, it's not as clear, but this actually will be connected to, I think Kathy did mention this. It will have to do with the minimum exponentials, right? Because notice that the first the probability exponential lambda 1 is less than lambda 2 actually is equivalent to saying the minimum of them is the first one, right? So when you compare, right, at least two numbers, in some way you're referring to the minimum, right? So the order statistics here of the exponential will become relevant, okay? And also, if you want to generalize this to, let's say, a K servers model, let's say there's Mr. U here, Mr. V there, whatever, right? Then notice that, and let's say they all have different rates, and notice that the minimum of the exponentials will still be a very much relevant quantity to look at. You know why, right? Because the model says Mr. X will go in, right, as soon as one of the server opens up. Of course, the server will open up at the minimum, right, of the serving time of all these random variables, right? So that's kind of like leading up to point out why like the minimum of the exponentials, right? The waiting time, the serving time is a relevant quantity that plays a role, right, in queuing model. Okay, because it decides basically the time that a item in the queue, right, will get to move up into the servers, right? For all items, actually, right? It's all about a minimum serving times, right, of all servers, correct? Okay, so that's part A, right? That's sort of like the items to pay attention to. Well, part B, what would be the difficulty or maybe easy? Who knows? What is part B? When Mr. X is already being served, and right, Mr. Z comes in, right? Oh, sorry, Mr. Y comes in. Whatever.
Quick question about part A. So if we're
Mhm.
actually gonna take time and compute this probability, should we go about it by conditioning on one
Yeah,
and
yeah.
two and then using the
Here,
law of total probability or something?
yes. But there is basically easy thing to do about the minimum or the order statistics and maximum order statistics. You know the PDF. That's one thing. Second, right? These are independent, so conditioning is not necessary because right? These are independent, so literally, probably two random variable x less than y is the double integral over the region x less than y of fx times fy because they're independent.
Oh, that's nice. Okay.
Yeah. But you'll see that the answer actually is very, very simple here. If I remember correctly, it'll come out to be this. So again, right, from exponential being exponential with very nice properties. But yeah, I mean, to address your question, in general, these are not that hard calculations because they're independent. So the PDF split. Yeah.
Thank you. Okay.
Sure. Okay, so for part B, right? What do you think the difficulty is, or what would be the challenge if Mr. X is already being served, and then Mr. Y comes in, right? Last. I mean, comes in, right? Then to ask the problem, Mr. X will be a last to leave. What will be the difficulty?
Well, here you're using the maximum, right? Instead of the minimum.
Oh.
No.
No.
Okay.
So first of all, right, it's not that to begin with. So several things, right? It's good that you mentioned a maximum because I guess that's a natural thing to think about if we have a minimum. But if you think about it, right, first of all, the maximum has not much of a role to play in a queuing model like this, right? Again, because we have three customers, right? So somehow probably the maximum makes sense in the question in some way. But if you generalize it to like a general queuing model, right? Then think about it. Basically a maximum at any point will simply be the time, right? At any one point where all of these guys, right, finish with their customers. But right, the point of a queue is that as soon as one of them is finished, it'll be filled in, right? Assume an infinite queue, meaning that the queue is never empty or things like that. So, right, unless you have an empty queue, meaning there's no person waiting here, right? Then the maximum kind of represents the closing time or something. But if you always have a queue, right? I'm not so sure if the maximum means anything in terms of moving up the line, things like that, right? So that's one thing to just say. But the second, so that's from a conceptual point of view. The second is from the technical point of view. the maximum between two exponentials actually have nothing nice to be said, right? Actually, the minimum of the two exponentials is an exponential, right? With rate, I think, being the sum of the two. The maximum is not an exponential. So even from a technical point of view, the maximum is not that nice to play with. Not that, right? Of course, being technically unpleasant to work with is not the reason why we don't work with it. But I think either way, right? Here, the maximum doesn't play as much a role in queuing model. Now back to the go ahead.
So X and Z are serving and Y enters late in this scenario?
Correct.
Okay, yeah.
Exactly. So right, and also it's also for this question, it's also unclear what the maximum. Oh, by the way, right? For part B, we are back to the same rate, equal rate, lambda. Okay, and you will see that part B will actually be a very complex question if the rates are different. Not very, but harder. Okay, part B will be same rate. But even under the same rate, right? I think it's kind of probably makes sense that the maximum doesn't seem to play a role. Because if you take the maximum between exponential and exponential, right? At most you get the time when both servers finish with both of these guys, but that doesn't correspond to Mr. X finish last, right? So no, I don't think, right? Either way, the maximum doesn't seem to be the variable to look at.
To rephrase the question, X is last to leave. That's the same as the scenario where Z finishes before X, correct? And
Yeah,
Y finishes before X.
correct, exactly.
Yeah.
There you go, good, right? So what would that be? So in some way, right, you see in part B, it's like probability X is bigger than Z plus Y. Agree? That would be the probability X finish last, right?
Wouldn't you also have to include in that, like, my suggestion for this problem was that probability of X is greater than Z plus Y and X is greater than Z.
Yeah, but if X is bigger than Z plus Y, then automatically X is bigger than Z, right? Because Y is a non-negative random variable. So you don't need this, right?
Okay, thank you.
No worries. But a surprising thing here, right? And I would say surprise, or special with a capital S, is that this will be this times that. Now contemplate a little bit and see why. Special because only works in this scenario, right? I don't want you to go around and advertise that I say this is true in general. But do you see why it's true in this context?
Would it be true because of the memoryless property?
Exactly. However, right? And however is the memoryless property in this case only works because they have the same rate, lambda. I'll show you, right? These two servers right here. If they have different rates, then the memoryless property won't work for part B, right? So like I said, right, it's very natural or not, I don't know, to throw this kind of calculation in for part B, right? Because you say, well, it's memoryless, isn't this true? It's true in the case when the two servers have the same rate lambda, and it won't be true in general. Of course, right? This quantity is always true, whatever you want to calculate out to be. But you want to reduce it down to this. This is only true if the two servers have the same rate lambda. Okay, so we'll show you. But again, right? So the point of me discussing all these variations is to show you what tools to make you think about what tools we need to work with queuing models and the pitfalls or the let's say the subtleties, right, of the memoryless property that yes, in general we can use memoryless, but we kind of trust that too much, we might fall into something, right? Okay, so let's take a look. So the first thing, right, is as we mentioned, that the minimum of two exponential will be an exponential with rate being the sum, right? The reason is because of the, order statistics, right? The minimum is bigger than or equal to something, means that both of them have to be bigger than something, right? And then both of they're independent, so it's a product. Okay, so it's very easy proof. This is the order statistics kind of move, right? That the minimum of the independent variables, right? And the probability of they bigger than something is a product, right? Of all of them bigger than something, right? By definition of minimum and independence. And of course, right, this is structure exponential, that's why. Okay. Now the probability that T1 is the minimum will happen to be something like this, right? And here, well, we'll skip the proof, but basically, I think is there a quick way to do this? Nah, I mean, or just integrate out, right? Let's the boring derivation, right? This is easy, so we'll show you. But this one, you just kind of integrate out and get lambda 1 over lambda plus lambda 2, right? And so the probability, right? The conditional expectation. So notice, right, that knowing that T1 is less than or equal to T2, right? Knowing that T1 is the minimum, then the expectation of T1, right, will just be the expectation of the minimum, which is the 1 over lambda 1 plus lambda 2. So in other words, right, if you know that you are the one who finished first, then the expectation of the waiting time, right, is just really the expectation of the minimum. Okay. So that's sort of like the preliminary about minimum, right, of exponential and comparing to independent exponential. Any question about this? All right. And this is a slide to talk about the maximum not having any nice pattern, right? So you can still do it. You can still find the CDF. You can still find the PDF. And you can work with it. It's just not exponential. Okay. Notice this actually has some sort of like the inclusion exclusion flavor, right? A plus B minus minimum, right? So anyway, I'm not gonna comment too much on that, but yeah, actually this is exactly by the linearity expectation, right? Because the maximum of two numbers plus the minimum of two numbers is exactly the sum of those two numbers. That's what, right? You subtract the minimum, you get the max. But anyway, right? The maximum is not an exponential, and like I said, not that I want to claim definitively it or never has a role to play in Q model. Is rare, right? To have Q maximum to play and to come in Q model analysis. All right, any question? Okay, so all right, so now having said that, right? Anyone wants to guess the answer to case A? Knowing that, right, the probability of exponential lambda 1 is less than lambda 2 is lambda 1 over lambda 1 plus lambda 2. What do you think the answer would be? From probability means the X finish last. So let's say, right, this is Y, this is Z, right? This is rate lambda 1, this is rate lambda 2, this is Mr. X, right? What do you think is the probability Mr. X finish last?
Clarification. When it says Mr. X inherits the rate, does that mean of the server that he replaces?
Yeah. I think inherited rate just really means that the server doesn't suddenly see Mr. X as like, very much in a hurry, so they change the rate to accommodate Mr. X, right? I mean, that actually also is a thing that could happen with servers, meaning, right, server could have different rates for different customers. Again, right, variations, but not, right, same rate. So the word inherited rate just really emphasize that the server keeps the same rate for every customer. Well, right, clearly Mr. X will come into server one with server, let's call Mr. Y, right? It's server one, right? Mr. X will come into server one with probability lambda one over lambda one plus lambda two, right? And then what happens?
Then X has the same rate as Y, which is lambda one, and you
Mhm.
want the probability that Z finishes before X, so that's lambda two over lambda one plus lambda two. And then I guess you have to consider the other case and then sum them.
Yeah, the other case I think is the same thing, right?
It's the same thing, yeah. So
So that should be the answer. Do we agree?
that looks right.
Yeah. Any question about this? All right. So now let us take a look at the second case, right? So this is the case when you have Mr. X here, right? I guess mix X and Y, right? And Z is coming in, right? Okay. So as we mentioned, right? The answer here will be 1/4. But the memoryless property, right, acts slightly differently. Okay. And it relies on the fact that the two servers have the same rate. And here's the reason. Right? If you have three exponentials that have the same rate, then, right, knowing that the first one, right, so think of this as Mr. X right here, T1 represents Mr. X, right? Knowing that Mr. X has survived Mr. Y, right? T3 is Mr. Y. Condition on that, right? And then, so then the probability that Mr. X will survive Mr. Z as well, right? Is the probability Mr. X survive Mr. Z, right? And that's the memoryless property. Okay. Now, this is true because of this, meaning that, right, you deduct the time that Mr. X has, spent, right? Wow, right? If Mr. Y is being served, Mr. X is also being served, right? So it's really about, right? If you look at the remaining time of Mr. X, then that's still an exponential. So that's why, right? It works that way. However, if the rates differ, then what this is no longer an exponential. Notice, right? The difference is this. If you subtract a deterministic quantity, it's exponential. But if you subtract a random quantity, then it only works if that random quantity has the same rate as x, as the one you subtract from. And that's a subtlety going on here. Do you understand? So that's the thing we want to point out, right? That basically the exponential structure is not preserved if you condition on surviving a random amount. Yeah. So in general, you have to work with basically, the general expression of working with conditional probability. Any question about this? Right. So, just to recap, mostly, the queuing model works, with memless property, Basically, as soon as the server starts with a new customer, then it's as if, all the other servers get refreshed, with the time, Because, memless, But you have to be careful sometimes when you replace it, with the random time. Okay. All right. So now let's move on to then a new topic, not a new topic, but this is going to be like generalization, okay, of the rate lambda. And number one, critique or not, is up to you how you want to look at it, so the memless property is super nice, It allows us to just renew, without thinking much about, whatever, A lot of phenomenon in life is not renewed, It has memory. Like I said, Aging doesn't seem like a renewable process, You have memory. Your body has memory of how much it has survived. So to generalize this, okay, then the concept of hazard rate, which, well, of course, we'll use hazard rate in this lecture, but hazard rate is actually very, very common in actuarial science, because that's where they model, fatality, people's life expectancy and things like that. Now, so basically, the thing is, you start out defining what hazard rate is, etc. But I think probably, is more intuitive to look at the exponential case first, and then you understand the point of hazard rate, Basically, the exponential random variable, the hazard rate is constant. It doesn't matter what t is. So okay, let's go back to the hazard rate. The hazard rate is actually very intuitive. It's the density, over this. But this is the definition, but that shouldn't scare you. It basically, is the survival probability, and the density really can be interpreted as approximately, or is the instantaneous, likelihood of you surviving at that moment, So the instantaneous likelihood of you surviving at that moment divided by the over, the remaining, survival time, survival probability sounds like, a good definition for the hazard rate, So it's really about this conditioning right here, Suppose that you have lived up to time t, what's the probability that you will live, in that tiny bit, of length of time in the next instance, And following this definition, then you see that the exponential has constant hazard rate. And that exactly is the reason why it has memless property, or memless property is equivalent to constant hazard rate, And hazard rate, again, doesn't have to be super fancy. It's really the decaying rate, Meaning that the decaying rate of the likelihood, If the likelihood decays at constant rate, at every time instance, then clearly you have no idea where you are, just looking at the decaying rate. But if suppose, let's say, the longer you survive, the faster you decay, like human aging, whatever, then you should at least make lambda depends on t. That's all there is, And then in that case, you lose the memless property. Okay. And the thing is, and this statement right here is of course very interesting probability, but the actuarial people would appreciate this statement more. Meaning, right, that basically defining this concept, by the way, that the concept hazard rate clearly only applies to continuous distribution, right? Because of the density, it doesn't apply to discrete distribution. But the actuarial people would say, right, this is exactly the reason why they can focus on hazard rate, because the hazard rate is equivalent to the distribution, meaning that when they say they want a certain hazard rate, they top a unique random variable with that rate. No confusion there. Okay. Any question about this? All right. So good place to take a break, right? Let us continue at 11:35. Okay. So like I said, no quiz. We're just gonna continue at 11:35. let's continue, right? Any question before we continue? Okay, so let's look at this, right, which is I call a hyper exponential model. Let's see here. Okay, so what is it? And there are many occasions, right, where this hyper exponential model would arise. This is just a story that we told, but basically, right, suppose you have like n, right, exponential clocks, right, n customers, whatever, right, n servers. So here it tells n batteries, right, and basically you would use, right, a certain clock with a certain kind of probability. All right, and so you want to know, so basically you randomly select a clock, right? This is exactly it. You have n different clocks, and you randomly select a clock with probability pi. Okay. Question: what kind of distribution do you have, right, in terms of your clock? Does that make sense? So here, right, the story of the battery is you have like, a box of n types of battery, right? And you just randomly grab a battery to use with some probabilities, right? I guess depends on how many of the battery of that type you have in a box. So when you use that strategy, right, then what is a lifetime of or what's the hazard rate, right, of the quote unquote, right, of the lifetime of your device? Does that make sense? So if you use a definitive battery, right, then the hazard rate is lambda I, right? But if you randomly select the batteries, then what's the hazard rate of your lifetime? Okay, does that make sense? And what's the answer? The answer, right, is that basically the probability, right, that y less than or equal to y, right? Of course, this is really just by the law of total probability, right? You see, and there, that's exactly it, right? This is the survival time of each exponential of type I, and then this is the probability you select the type I, right? But so this is the CDF, and right, of course, you can differentiate to get a PDF. Why do we bother? Because, right, remember the hazard rate is a ratio, right, of the PDF over the 1 minus the CDF. Okay, and so the hazard rate will be this quantity. Okay, and that looks like a bunch of formulas, meaning who cares? A sum, follow formula, right? And of course, that's the thing, right, that we most easily fall into when we derive stuff, right, with new concepts. But you will never get anywhere, right, if you just look at the formula and say, yeah, right? We want to understand if the formula makes sense, if it tells us something, right? And here, one way to try to tease out the meaning for this hazard rate is to try to see what the limit of the hazard rate is as time goes on. Okay, why so? Or why this move, right? Well, you see, right, I guess mathematically you could kind of surmise that something will come out, right, of this if I take t to infinity because of different exponentials. So that's just purely from a mathematical point of view. You're so experienced with math that you know that if I take the limit, something comes out. But from the meaning point of view, right, it also makes sense in this way, right? If you know what hazard rate is, which is really, right, the decaying rate at a certain amount of time, right? And the exponential being constant, so this limit, right, will be a constant number, right? If you just use the good old exponential. So you want to see, right? I mean, okay, if the hazard rate is any different for if we have a really generally a different random variable than the exponential, then right the long term, you can see this is like the long term limiting hazard rate, if you will, right? In the end, there's a hazard rate settle to something. Does that make sense? And yeah, it might tell you a story, right? So this is why the asymptotic analysis sometimes reveal the meaning behind the formula. Okay, that's the best I can say about why we do this. Because if you, like I said, if you just stay with this, right, then that's fine, that's correct, but almost meaningless, right? What is that? But anyway, so well, having said that, right, what do you think this limit is? I mean, this is just good old calculus, right? What would this limit be?
The lambda I just pulls out from the sum, right, as a constant? Or oh, wait, you can
Absolutely not.
wait,
No.
it's sub I, it's sub I, I'm so sorry.
Yeah. No. It's not constant lambda. It's not the same lambda. If it's the same lambda, then we have no
Oh my
story
God,
to
I
tell.
thought this was so easy, and then I was like, no, never mind.
No. So there are a bunch of, right, to recap, there are a bunch of different lambdas, right, with their own exponential life or exponential hazard rate, whatever. No, exponential life, right? Exponential density. And then multiply with the PI, which is the probability of them being selected. So if I take this limit, right, what will I get? It's actually very simple if you think of the dominant term, which is exactly what someone who's kind of like familiar with exponential would know right away, right? When you have a bunch of exponential competing, okay, and when you push things to infinity, then because exponential decays very quickly, even if the rate changes a little bit, the only thing that stands out, okay, is the one that is dominant. So when you have the ratio like this, right, then basically it will be the ratio of the dominant term of each, which is what? What is the dominant term of each sum? The dominant term is e to minus lambda I t for lambda I minimum, or the really minimum lambda I. Agree? The smallest lambda I will have the largest e to minus lambda t. It's so large, right, that it will be the only term that you see in the sum when you push t to infinity. Does that make sense? So when you take push t to infinity, the only term that survive is p, that's called lambda min. Sorry, pi min, right? Not p lambda min, but pi min. Lambda min e to minus lambda min t divided by that. Right. Long story short, this will only give you lambda min. Is that okay? So that's the calculus. Now, does this make sense in terms of interpretation, in terms of battery life? Yeah. Does this make sense? Why is it that for this selection strategy, right, the long-term hazard rate or the limiting hazard rate is lambda min? Actually, right, is in this case, right, just so you remember, is lambda min a good thing or a bad thing in terms of survival? remember in our model, right, exponential lambda will have expectation 1 over lambda. So the smaller lambda, the larger the life expectancy, right? In the convention we use. So lambda min here actually is the good thing, or exactly lambda min is the one with the longest expected lifetime among all the clock of all the batteries. Okay. So here the math says that in the long run, the hazard rate of this strategy will be the same as the hazard rate of the battery with the longest lifetime. Does that make sense? Or does the calculation make sense? I'm not saying like this. Okay, first, do you understand my statement? But B, does it even make sense with the strategy? Like, does the strategy seem to work out that way?
Can you qualitatively assign a meaning to lambda? I
Yeah.
understand the math.
You can, and that's the whole point. That's why I was trying to make you guys see. Lambda represents, bluntly speaking, your case of dying, your chance of dying, your likelihood of dying, if you will, right? Because you see, the hazard rate represents the chance of you failing at time t, supposing you survive there, right? So the hazard rate being lambda, right, for the clock exponential. So if lambda 1 is less than lambda 2, then supposingly that both of them have survived at the same time, then the lambda 2 guy has a higher chance of going than the first guy. Put it that way. Does that make sense?
Okay, yeah, I'm sold.
No, it's fine. Well, no, yeah. But notice things are very complex here, and you could really interpret hazard rate in the wrong way. In the sense that, okay, you have two persons, right? One has higher hazard rate than the other. Does that mean that the one with high hazard rate will go first? What that means? No, right? Because everything being random, this is just condition on both having survived with the same amount of time, then the likelihood of one surviving in the next stage is higher than the other. But right, things being random, you cannot say definitively this will less than that, right? But this is about the likelihood of survival, right? Instantaneous survival. So hazard rate is a very delicate object to analyze, right? Or to understand correctly. But it does represent that instantaneous, right, survival probability, supposing you have lived that far. Okay. So back to the battery story, right? Does this make sense? And the answer is yes, right? But almost in a trivial way. Because when you take t to infinity, what are you saying? You're saying that condition, right, on the lifetime has already lived a very long time, right? So meaning, let's say you use this strategy and you notice that, oh my gosh, I have been using this battery for 10 years and it's still going. Then what this math says, well, very likely you use the best type of battery, the battery with the lowest hazard rate. That's all there is, right? So the pushing t to infinity here does not guarantee that you will select the battery with the longest expected life expectancy or the lowest hazard rate in any sense. But it says that conditioned on the fact that your strategy has worked for a long time, that is most likely, or it must be the case that you have used the best battery model possible. That's all.
Good question.
Do we understand? Yeah, go ahead.
Is there an application of the hazard rate to math finance?
Not finance, my area. We don't use survival time a lot because for us, it's all about default probability and things. I guess if people do risk analysis, they might. So one thing is, right, actuarial science and my area are two not very much connected areas. People kind of think we do the same thing, but we don't. Insurance people, right, have, like I said, have a very big interest on, right, modeling survival time of things, right, and how likely it's going to fail. For us, again, right, so notice it's not something you can say definitively, because at the end of the day, where was it? Hazard rate and distribution are one and the same thing. So, right, but like, so I would say hazard rate shows up more in risk management, because again, right, the risk of failing and the risk of you going bankrupt, that kind of thing, right, is there, right, implicitly in hazard rate. But again, risk has many types, and actuarial risk is different from financial risk. And as you'll see, my area is more about, I don't know, option pricing and things like that. And is a very, very long story. It takes a whole class to explain. And so, yeah,
Yeah.
long story short, I don't see.
I was guessing maybe it would show up with CDSs, like credit default swaps. But
So maybe, again, right, depends on the model you use. And also, like I said, I can see it shows up in terms of default probabilities and things like that, right? And so if you have a default probability, you probably could come up with a hazard rate notion to measure something, right? The rate of defaulting at certain kind of level, right?
that makes sense.
Yeah. So like I said, right, if you understand the meaning of this, then T here doesn't have to represent time. It can represent a level, right, of something where you start to fail. But question is, do you formulate your model in that way so you can use, so that the hazard rate is appropriate, right? Is really, yeah. So yeah, I guess long story short, risk, anything you do with risk probably can use this in a meaningful way, but how and why totally depends on the model. Okay, sorry. Yep. So that's that. So that's hazard rate, right? Any question about this? So I guess, right, to recap, hazard rate is a generalization, right, of the exponential model, right? So basically, the moment you move into a dependence of lambda on time, then you are talking about hazard rate, and you can do that. That's actually just the point of this story in a short few sentences, right? So always keep that possibility in mind, that, right, the rate of waiting in line or the rate of serving could change, right? For example, a very easy model is, right, when you look at people arriving in a queue, right? Post office, whatever, right? This is a queue, right? What could happen is, right, that people arriving at the queue, the rate of arrival changes, right, throughout the day, correct? In the morning, you don't have a lot of customers. Around noon, you have a lot of customers, maybe higher chance. And then, right, probably toward the end of the day when people start leaving work, I'm not sure, right? But it's kind of clear if you observe any queue, any post office or at a supermarket, right? Probably the server rate, you can argue is constant, but the queuing, right, the arrival rate definitely changes during the time in the day. So when you have that, then, right, the exponential clock may not be appropriate to model, right, arrival at a queue, right? You want to use hazard rate or something that changes with time. All right, so the next few slides just kind of generalize what we talked about before, right? Because I guess we've been playing with toy model with, two servers, right? And no one in queue or one person in the queue. You can have like a lot of people in queues with more than two servers, right? So the generalization, of course, is with the minimum, right, of n independent exponentials. Well, right, the result should not surprise anyone. Basically, sorry, I look at the wrong slide. This one, right? The minimum is just the exponential of the sum, right? And the probability that a particular clock is the minimum is the rate of that clock over the sum. Okay. So that's a generalization, right, of the two exponential clock model, right? And here is the thing that is important, right? And this exactly, right? This property right here. Okay, let me pause here a little bit. See if you can read this math, right? Because if you sometimes it's just a formula. If you understand this statement, explain to me in the queuing model we've been doing so far, explain to me how this property is crucial in queuing analysis. Where would this be used? Right? It says that the order, or yeah, right, the exponential, right, is independent, the order of the exponential, right? The residual are independent of the exponential of the minimum. Where would this result be relevant in the Q model? And I would argue that without this property, right, the Q model will be super hard to analyze. Any guess?
It doesn't matter who leaves first in a waiting time scenario with the servers.
That's correct. That's exactly it. Basically, this, and not only that, right? This is exactly the swapping of customers in a queue, right? So remember I said, right? If you have queue 1 to 5, whatever, right? And then you have a bunch of customers waiting, right? Then clearly, right, the one who leaves first will be the minimum of the exponential. Now, and then, right, then the next one will fill in, right, the empty spot. And what you would like to say, well, and then life goes on again. Well, you wish you want, right? You could, but that's not always true, right? As we saw, right, with the special case above. So this is true because remember, this is a remaining time, right? So suppose that the swapping happens at kiosk 3. Then the remaining time for the remaining kiosks are still exponentials and independent, right, as before. And of course, swapping kiosk 3, so it's still that this guy will take on a fresh independent exponential. So of course, you will get all exponential clocks renew again, independent, right? This is exactly Markov property, but the most beautiful one, right? Strong Markov property, whatever that you can use, right? Imagine the terrible mess you will have if, right, somehow suppose that they're still independent. That's you're lucky, right? Somehow, if you replace this, they're still independent, but they're no longer exponential. That's easily happened, right? Because the minimum, right? They interact with the minimum somehow. So if that's the case, then already, right, you have difficulty updating your model, right? So that's exactly the key. Okay. Any question? All right. So you can verify this with 2 variables, right? But easily done with n variables. Any question here? All right. So here, right, basically just repeating, actually this slide and the above slide say the same thing, right? But just, in a different ways. So if you have exponential, then the minimum, right, does not, I guess, well, I guess this is more important, but basically, right, the how the TIs will come out, it will be independent of what the minimum would be, right? That again, right, has the effect of like, again, right, which one will finish first, which one will finish last, kind of thing, right, in the server stuff. more than 2 servers, right? Now, this actually, right, is connected to the one I was mentioning for that. Do not take these properties for granted, right? They sometimes depend on very much special properties of the exponential and sometimes even equal rate, right? Let's take the dice, right? Which is really not, dice are like uniform, right? Clock, not independent clock, right? If you take 2 dice, then the probability that one is higher than the other, right, is you know, I guess because of the high, right? That's why it's slightly less than 1/2, right? Whatever. But if you do know the minimum, then the probability one finish less than the other is much less. It's changed. Do we understand? So of course, right, this is just really an easy example you can verify for yourself, or you can work with this on a continuous uniform. But the point is, right, the uniform is not memoryless. And right, knowing the minimum will affect how the order or the calculation, the distribution of T1 and T2 behave. Does that make sense? So this again, right, gives a very strong reason, even though maybe a sneaky one, that the exponential clock, exponential model is the right model, right? Right as in like makes our life much easier to analyze server time and queuing time and everything like that. Right. I mean, if you assume that the server serve with uniform clock, right? Uniform, let's say 0 to 10, wouldn't that be nice? Like you go to a checkout line, right? And it's guaranteed that the checkout will be finished within 5 minutes, right? That's uniform, right? Okay, that's nice for at least me. Maybe I like that kind of thing, but the calculations will be super ugly, right? The distribution will keep changing, updating depending on the conditioning, that kind of thing. Right? Any question? All right. So this is an application, right, of that property, right? Back to the post office problem again, right? So if this is the Mr. X arriving, right, after, right, Mr. Y and Z has already being served, right? Then Mr. X waiting time, right, will be the minimum, right, of these two, and the waiting time is 1 over that, right? So we know this already, right? The probability that Mr. X has to wait at the post office is an exponential, minimum exponential. But right, this is easy part. The more complex part is Mr. X service time, right, and the total time he spent at the queue, right? So Mr. X service time will be exponential lambda 1 if he goes to first server, and he go to exponential lambda 2, right, if we go to second server, right? And so the total time he will spend at the office is that, right? And notice, right, we have used the independence here, right, to work out the distribution of Mr. X service time. Does that make sense? Any question about this?
What's the conditional expectation? Like S given, suppose Y finishes first, so exponential lambda 1. I'm just trying to work out the calculation for expectation of S in my head.
Sure. So let me say this, right? So S really is a hyper exponential. Like this battery. story here. You see? That's really it. Sorry, what was it? Do you see? So in fact, right, that's another lesson here. For a customer waiting to be served, right, at the top of line of the queue, right? 1, 2, 3, 4 servers, and this is the customer, right, waiting. Then the serving time of this customer will have a hyper-exponential distribution. Correct? Because he will go to whichever server that finishes first. So he will select a battery, right? He will set a lifetime with a random probability. What probability? The probability that that server will be the one that is finished first. Do you understand?
Yeah, that makes sense.
So yeah, right. So the hyper-exponential, right, is not just a hypothetical description here. It's really here. Right. So I think that's really what you use to work out the distribution. So it's just really the law of total expectation. All right. Any other question? Okay. So let's finish this lecture, right, with this model, right? So this is not your typical queuing model like MM1, MMK, that kind of thing. Because in those queuing model, right, the customers never leave. So it's probably more appropriate for like, server, like online server, I don't know, networking, that kind of thing, right? Because I guess when you send a packet, the packet doesn't say, okay, I'm waiting too long, I'm leaving. Maybe it could, I don't know, right? But with live customers, right, that could happen. But I'm saying what the traditional queuing model, when you read MM1, MMK, that kind of thing, I think the built-in assumption is the customers in the queue never leave. So just to say that, right, what we're discussing here is a realistic model, but I think it's not within like the classical framework of those queuing theory. But I guess someone will have a classification for this anyway, right? But so we have a single server and we have customers, one customer already being served, right? So S, and there's a queue, right, of N people. So now the server takes time mu to serve, but every customer is here, right? If they wait beyond their tolerance, then they will leave, right, the queue. And of course, right, the queue will just move up. All right. Is the story clear so far? So, right. So we want to, let's say if you are a person in a queue, right? So, and here, I guess we should use a different notation maybe. Position K, right? Because here we don't mean the last person, but any kind of person, right? If you are the third in line, what's the probability that you will serve, you get served, and what's your expected wait time, given that you are served, right? And notice here, right, why is it a conditional probability, conditional expectation? Because, right, I mean, if you leave, then there's no serving time, right? So given that you actually get served, right, what's the expected wait time? Okay. All right, cool. So let's see. Let's maybe hone in on this guy first, PK. What do you think? What would be the analysis for this PK? Suppose you're the kth person in line, right? What's the probability that you will get served? Actually, what's the trick here? Oh, what's the trick? Not a trick, right? What's the technique here?
Well, you have to, like, you're at some kth position in the middle of the line. So you have to essentially get up to the first position.
Yeah, good. exactly.
So I'm not sure how to consider all of the other ones either leaving or being served.
Yeah,
Like-
okay.
Distance 1 to k minus 1.
But so what should you do first in this kind of scenarios? So here's server, right? Here's a queue, right? And you want to ask for PK, right? I guess the technique here, which is a very small one, it's not even called a technique. You start with a simple case first. See if you can answer that, right? And build up. What's the simplest K we can answer for?
K equals 1.
Yeah. So what's P1? So to remember, right? Each one here is exponential theta. This is exponential mu, right? So what's P1?
The minimum between exponential mu and exponential theta.
Yeah, the probability that, right, exponential mu is less than exponential theta, right? The server finished before this guy gets impatient, right?
Oh yeah, yeah. You don't want him. You don't want the other.
Right.
Like-
So the answer is mu over mu plus theta. Agree? So that's the easiest one, right? We got that. Any question? Well, P2 though. How do we analyze P2?
My confusion is when you're considering the people ahead of you, right?
Mm-hmm.
Which is only
Yep.
one person.
Yeah, that's the key. Yep.
e- Either that person gets really frustrated and leaves.
Yep.
So their exponential theta is somehow less than yours, or they get served and you're still waiting and then you get served. Is that the are those the two branches that you're considering?
Right. So here's the thing, right? What you're saying is, well, if you want to think about the probability that you get served, right, for the second person, there are a lot of scenarios to consider, correct? So why don't we simplify the question for P2 in this way? Instead of asking the probability the second person gets served, what should we ask first?
Is the first person leaving or is the first person getting served?
No, because we don't know that already, right?
Okay.
So I would argue for the second person, what's the relevant question that they should ask? I would argue, any input before I give you the answer? I would argue the probability that the person moves up to line 1, right? Meaning that, well, if the person is going to get served, he's got to move to position 1 first. Agree? Then we will look at the probability he gets served. But if we cannot answer the probability he moves up to line 1, right? Then, do you understand what I'm saying? So let's simplify the question to the probability that the second person moves up to position 1. What would that be? So he will move up to position 1 if his exponential clock, right, is less than what? The serving time, right? If the serving person is finished before he gets impatient, he will move up, correct? What else?
When you say his exponential clock, are you referring to person 2?
Person 2, yeah. Right? Or what? Or his exponential clock is also less than, right? So this is all exponential data. So sorry, let me do this. So let me call WI, right, as the impatient time, right, of customer I. Okay? And let me say S as the serving time. So probability that 2 moves to 1 is probability that W2 is less than S, right? That's what I mean. Or W2 is less than W1. Do we agree? Now, we can do inclusion, exclusion here, right?
When you say S, are you referring to the total serving time for both customers 1 and 2?
No. Only serving time of the current person.
Okay.
Right? You see, because, right, if, oh, sorry, this is bigger.
Okay, that makes more sense.
Yeah, so sorry. I said exponential meter. I apologize. I really apologize. S is less than W2, right? Or
W1 is less than W2, right?
yeah, I'm very sorry. Yep. So in fact, right here, I guess probably what I want to say is so we can do inclusion, exclusion here, right? But what would be the complement of this? W2 is less than. Do we agree? Does it make sense? Because this is the same as W2 is less than S and W2 is less than
Oh, yes, I
W1.
agree.
Or, right, what I'm trying to say is maybe what's the probability he does not move to line 1? He does not move to line 1 if his impatient time is before the server is done, or his impatient time is before the end, or yeah, right, and before, right, the first customer is impatient, right? Then he will leave first, correct? But otherwise he will move to line 1, right? Now, why is this a good formulation? Because the minimum S and W1 will be a exponential of theta plus mu, right? Which is independent of this exponential theta. So the probability will be 1 minus theta over 2 theta plus mu. Correct? So see if we can simplify this. 2 theta minus, so it's theta. Yes, you agree?
Yeah, that looks right. And you can generalize this, I guess.
Yeah, but let's see, right? Then the probability to get served will be what? Probability to get served condition on 2 moves to 1 times P 2 moves to 1. Right? Otherwise, 2 will not get served. So we don't have to look at the other case. Correct? Which means, if 2 moves to 1, then 2 becomes 1. So it's mu over mu plus theta times theta plus mu over 2 theta plus mu. Right? We understand now?
Yeah.
What about P3? Now we understand the analysis of P3, right? So it'll be a product of what? 3 moves to 2, and then 2 moves to 1. 1 goes to 0, if you will, right? 1 gets served. Right? And let's see, right? What's the general analysis here? General analysis here, you see, will always be 1 minus, right, the probability of an exponential theta, let's say the kth person, right, less than an exponential of k minus 1 times theta plus mu. Agree? Because that's how many people ahead of him, right? K minus 1 theta times theta plus mu, which will be 1 minus, right, theta over k minus 1 times theta plus mu, right, which is k minus 2 theta, right, over k minus 1 theta plus mu. The point I want to say is, right, you see that the point is this will be a telescoping product.
Shouldn't it be k minus 1 in the numerator and k in the denominator instead of k minus 2 in the numerator and k minus 1 in the denominator?
Say again, you say this should be?
I was just thinking maybe it should be k minus 1 instead of k minus 2 and just k instead of k minus 1, like an off by 1 thing.
Oh, am I? So
I
I'm talking
mean,
about
that's just
k.
my guess.
So I'm
Because
talking about, no, you're right, because of this, right?
yeah,
Yeah,
that's what I was
no, I think you're right. So, oh, yeah, the reason is because when I do this, so I'm correct here. But when I move down here, I have to add this theta to this k minus 1.
Yes, you add the theta, and that's why it's
Yeah, that so it's k theta. No, thank you for that correction.
sure.
K theta. So I got k minus 1. Right, and then I will get yeah, okay, like that. So anyway, right, the whole point is this will be a telescoping product, right? Leaving us with mu over k theta plus mu. So that's a pk. Does that make sense? Any question? Okay, so I guess time's running out. So let me just quickly show you, right? So like that, right? That's the time, the probability being served. And the time, right, can be analyzed to exactly the same way. You just look at the expected time to move to the next position, and then you just sum them up. Because, right, I mean, condition on being served, then you must have moved up to the next line, next position in line to begin with. So, in a way, right, even though this problem sounds complex with people leaving and stuff like that, the moral of the story is, right, you just kind of look at like people moving up one spot in the line. right? And then updating the clock. So the thing that makes it easy again, right, is because of the exponential structure of the waiting time.
Quick question.
Sure.
When you move up from the kth position to the k-1th position, does your exponential clock reset?
Excellent question. You do. And again, right, that you mean your impatient time, right?
Yeah, your
Your
impatient
impatient
time.
time.
And that's why you can just keep comparing.
That is a beautiful question. Oh, sorry. Well, that's an excellent question. But that is exactly, again, this at work. You see? So yes, you're absolutely right. Right? Because and that's a very, very good point. Because, right, I mean, if your impatient time has memory, which is right, we all do, right? Then because you see, like, I mean, basically, right, the assumption is the 100 person in line, right, act in the same way in terms of their impatientness, right? No matter how long they wait, as long as they. So basically, it's like when they move up in line, they're so happy they forget to have they waited. I don't think so, right? We do have memory. So you point out a very, very good thing, very good, very, very excellent point. That basically this model is unrealistic in the sense that the impatient time has no memory, right? And we do have memory of how long we have waited, right? Something like that, right? So, but yeah, this model absolutely relies on the fact that the impatient time has no memory.
That makes sense. Thank you.
Yep. All right. Any other question before we stop for today? All right. So real quick, right? The plan for Monday, of course, we'll continue with Poisson process. We'll probably do a quick one of that, and then we'll do brand motion, right? A quick one. So hopefully wrap up certain things that expose you to these two things. Okay. Have a good weekend, and I'll see you on Monday.
Have a
Thank you.
nice weekend, Professor.
Thank you.
Yep. Thank you.
Quick question. So the
Sure.
final exam will go to lecture 10.
Absolutely. Just the homework. We focus on the homework. Yeah. These are
Okay, sure.
materials that will not show up on the exam. Yeah.
And do you know when we'll have, up until what date we'll have access to this Canvas site? Because after my final exams, I'd like to go back to some of the recordings.
Sure. So I do
when they'll
have
be
these
kicked out?
recordings stored up on my private YouTube channel. So as long as you promise not to spread this around, I
Okay.
can share that with you. Because I just, I'm still using these materials, right? And it's not like I want to make it proprietary or anything. But students, once they have access to these, they will feel they don't need to go to class anymore, whatever. Right?
Oh, I understand.
So,
Yeah.
so that's the only thing, right? So in the future, if you want to revisit these, I'll be happy to share that with you, right? But
Sure.
just
Thank you.
don't
I'll
spread
try
it.
to watch it before they kick us out of Canvas. I don't know how long they
Sure,
usually-
I think you do have like 30
I
days,
think
if
it's like
I'm
a
not
few
mistaken.
days. Yeah. I
Yeah.
mean, the summer session ends August 15th. That should be fine.
Okay.
Okay. And last question. So I spoke, again, I think I mentioned before, I have a exam conflict
Conflict or
with,
something. Yep.
yeah.
Mhm.
So I spoke to the physics department and I don't know, they're being so unreasonable. They're like, no, there's no next day makeup. They at first asked me to take the final exam today, even before the lectures were complete. And I was like, no, like that's not ideal for me. And so
Mhm.
they offered me a makeup for the day before, which is fine. I can definitely like make that happen. But I
Mhm.
just wanted to ask if it's possible to have a next day makeup for this class so I can take physics like on the 13th. If not, I can stick with the previous day makeup.
You should stick with the previous day makeup
Sure.
because we also are very hard on this, and this goes all the way to the course coordinator, Professor Bonar.
Oh,
I
wow.
think you know him for some reason. But you took his class, I believe. So anyway, right? Yeah, this policy doesn't come
Which
from me.
professor?
Professor Mona, David Mona.
Oh, Molnar. Oh my gosh, yes. I
Yep,
took
yep.
his combinatorics class.
Of
Yeah.
course, he mentioned. So anyway, right? The point is, this is official for everyone.
Oh, okay. No worries.
That yeah, we strictly enforce the day and the time of the final exam.
Sure,
Okay.
there's no problem. I'll just take the previous day makeup then. I'll make
Okay.
that happen. Okay, thank you. Have a nice
Sure.
weekend.
You too.